Okay, here we are going to talk about the practical op-amp and the ideal op-amp, and we'll see the characteristics of the ideal op-amp from the gain perspective and from the input resistance and output resistance. As we said that for linear operation you need to operate in this region, right? In order for the op-amp or the amplifier to work properly, you need to operate in this region, which is the linear region. So you need the difference between Vp and Vn, between the inverting, non-inverting input and the inverting input, to be between negative VCC over A and VCC over A, the negative DC bias over A and the positive DC bias over A. This is in order to work linear. Practically speaking, so if you look at the practical op-amp, you will see that usually VCC is in the range of 20 volt. Sometimes it's 15, sometimes it's 10. Maximum, usually we use 20 volt. And the gain, the open loop gain of the op-amp, usually it's much greater than 10,000. It's greater than 10,000. This means what? This means that this region between negative VCC over A and VCC over A will be in the range of 2 millivolt, from negative 2 millivolt up to 2 millivolt. If you divide 20 over 10,000, okay, it will be in the range of 2 millivolt, which is very, very small, right? This is for the practical op-amp. So for the practical op-amp, the linear region is very, very small. It goes from negative 2 milli to 2 milli. And then the amplifier saturates, right? Ideally speaking, the ideal op-amp, it has a gain of infinity. It has a gain of infinity, which means what? If the gain is infinity for the ideal op-amp, then this point will be 0 and this point will be 0, which means that for the ideal op-amp, the curve will look like this. The curve will look like this. This is the relation between V output and Vp minus Vn. This is very weird. Why? Because we say here that if you want to operate in the linear region, which is this region, you need the difference between Vp and Vn to be 0. So here we lost the objective, because we need to amplify the difference between Vp and Vn. How come you say I need the difference between Vp and Vn to be 0, while we need to amplify the source, our source, or the difference between two sources, right? So how can you say that the difference must be 0 if you want to amplify? That doesn't make sense, right? That's why we will never use the op-amp as an open loop. We'll never use the op-amp with its open loop gain like this. Why? Because you need the difference to be 0 in order to work in the linear region. Otherwise, it will be saturated and this is not an amplifier anymore, right? So we'll never use the op-amp in the open loop circuit or in the open loop mode. What we need to do in order to solve this problem is that we'll connect the op-amp to some other circuitry. We are going to connect some other circuit elements, and then we connect our sources here. After we connect our circuit elements, these circuit elements with negative feedback from the output to the input, it will help to maximize the linear region a little bit. So it will help again to get a bigger linear region. Instead of having a linear region only at the 0 between Vp and Vn, the difference is 0 between Vp and Vn, this feedback, negative feedback from the output to the input, okay, will help us, as we will see, we'll discuss this later, it will help us to have bigger linear region, and we'll be able to use the op-amp to amplify our sources, or the difference between our sources, without any problem in the linear region. So that's why we'll have something later, we'll have something called closed loop gain, and we'll have closed loop circuit with some feedback. Anyways, what we need to do, or what we need to know now, is for the ideal op-amp, if you assume that it is working, the op-amp itself, without any circuitry, if you assume that it is working in the linear region, ideal op-amp means A goes to infinity. This means that Vp must be equal to Vn. In the linear region, so in the linear region, for the ideal, this is the ideal op-amp. For the linear region, Vp will be equal to Vn. And this is an assumption that's very important, and we are going to use it a lot, because later we are going to assume that the op-amp is working in the linear region. Of course, we don't know whether it's in the linear region or it's saturated, but we'll have to assume, and at the end we check. So we'll assume it's operating in the linear region. If you assume it is operating in the linear region, which is this region, then you assume that Vp is equal to Vn, because in this region Vp minus Vn is 0, then Vp equals to Vn. So this assumption is very important. Again, if you assume that an ideal op-amp, and this is the ideal op-amp is the one that we are going to use most of the time. If you assume that it is working in the linear region, then you use this assumption Vp equals to Vn. Okay, next. Vp equals Vn, by the way, means if this is Vp and this is Vn, Vp minus Vn, sometimes they call it virtual short circuit. It's virtual. Virtual means it's not real, right? There is no short circuit. There is no actual short circuit between Vp and Vn, but they have the two voltages, they are equal to each other, okay? So they call it virtual short circuit. It's not a physical short circuit, it's virtual, something imaginary, okay? In the linear operation. Linear operation can be ensured by negative feedback, as I said. So we connect some feedback resistors and some other circuitry around the op-amp in order to guarantee the linearity, okay? And when we solve any problem, because we don't know whether the op-amp will be in the linear region or in any other region, you have to assume and check. And this is the process that we are going to follow in many other topics in our course. Assume and check. So we'll assume linearity, and then we check at the end. How do we check? You check by looking at the output, whether it is higher than VCC or lower than VCC. If the output is lower than VCC and higher than negative VCC, if the output is in this region, then your assumption of linearity was correct. But if you assume linearity and you find that the output is higher than VCC, this means that your assumption was wrong, because the output cannot be higher than VCC. If you assume linearity and you find that the output is lower than negative VCC, this means that your assumption is wrong and the op-amp will saturate. So we assume and we check at the end. If the output is between the allowable range, then that your assumption is correct and there is no problem. Okay? Fine. Another thing is that for the op-amp, the ideal op-amp, the input resistance is infinity. The input resistance is infinity. So the equivalent resistance seen by the input terminals of the op-amp is very large in practice. So practically speaking, it's very large. It goes to 1 mega or more. Ideal op-amp, it's infinity. The input resistance is infinity. So for the ideal op-amp, the input resistance, which is the Thevenin equivalent resistance between the two input terminals, it goes to infinity. But if the input resistance goes to infinity, what can we conclude here? What can we conclude? If the input resistance is infinity, this means that if you connect any source between these two terminals, let's imagine that we are going to connect any source Vs between these two terminals, what will be the current? Is. The input resistance is infinity. Whatever source you connect between these two terminals, the current is supposed to be 0. So that's why we say that In and Ip equals 0 for ideal op-amp. So always, not only in the linear region, always the Ip and In, they are 0 for the ideal op-amp. So this is the second assumption that will be very important to us. That Ip equals In equals 0, and the first assumption was that Vp equals Vn. These two assumptions are very important because we'll use them in order to solve any op-amp problem that involves an ideal op-amp. Of course, if Ip equals In equals 0, then from Kirchhoff current law, if you remember Kirchhoff current law, if you remember this shape for the op-amp, we have IC positive, this is the DC current, IC negative, this is the negative DC current, this is the output current, this is In, this is Ip. If IN and IP equals 0, let's apply Kirchhoff current law on the op-amp, on this big node. IN plus IP plus IC plus IC minus plus I out equals 0, right? But IN and IP, both of them are 0. This leads us that I out will be equal to negative IC plus negative IC minus. So if you apply Kirchhoff current law here, you'll find that I out plus IC plus IC minus equals 0. Because IN is 0 and IP is also 0 for the ideal op-amp. Okay? So now we have two assumptions that are very important. VP equals Vn for the ideal op-amp in the linear region, and IP equals In equals 0 for the ideal op-amp in any region in general. The input resistance of the ideal op-amp is infinity. The gain, the open loop gain of the ideal op-amp is infinity. What about the output resistance before we end this video? What about the output resistance? The output resistance of the ideal op-amp is 0. Why is that? Why is that? Because the output voltage, the voltage that goes to the load. Let's imagine that we are going to connect a load here, R load, to this op-amp. Okay? We can, you can calculate the equivalent circuit R Thevenin and V Thevenin for the op-amp between this terminal and the ground, and you can write, or you can plot this circuit as R Thevenin and V Thevenin, where this R Thevenin and V Thevenin are the Thevenin equivalent circuit of the op-amp from outside. R Thevenin will be the same as R out, right? R Thevenin is the resistance that you see from here, from the output, right? Now, let's look at the voltage. Let's look at the voltage of the op-amp. The voltage of the op-amp, the output voltage of the op-amp, doesn't depend on the current. It doesn't depend on the current at all. The output voltage of the op-amp, the voltage of the op-amp that goes to the load, this output voltage that goes to the load, it doesn't depend on the current at all. It depends on what? It depends on the input voltage. Well, if the input voltage is here, the output voltage will be in this region. Otherwise, the output voltage will saturate at VCC. It will saturate at negative VCC. It doesn't depend on the current at all, which means that even if you change the current going to the load by changing the load, and if you change R load from 1 kilo to 10 kilo, the current is going to change. But even if you change the current from IL1 to IL2, the output voltage will not change. This means what? What does it mean that the output voltage doesn't change even if you change the current? The output voltage is constant, which is constant even if we change the current. What does it mean, Shabab? What does it mean? If you change the current, the voltage across R Thevenin or R output here must change. And if the voltage here changes, the voltage output must change. Unless the resistance here is 0. If the resistance here is 0, then the output voltage will be equal to V Thevenin regardless of the current, right? Regardless of the current in the load. Even if you change the load and the current changed, always V Thevenin will be equal to V out. But if R Thevenin or R output here, it has any value, let's assume that R Thevenin or R output is 1 ohm. Then if you change the current, the voltage across it would change. This is the current, I load. If you change the current I load, the voltage would change and the voltage output would change. But now we see that the output voltage doesn't change even if you change the current. This means that R output must be 0. R output must be 0 because the output voltage doesn't change even if you change the current. If R output was not 0, then the output voltage would have changed when you change the current. I will say it again. If R output was not 0, let's assume it's 1 ohm. Then when you change the current here, due to the drop here, the output would change, right? But now the output doesn't change when you change the current. This means that this resistance is 0. This resistance is 0. This is the only case that the output remains always constant even if you change the current, right? That's why we say that the output resistance of the open loop, and we'll see later that the output resistance of the closed loop, both of them will be 0. Because even in the closed loop, the output voltage also will not change with the current. So the output resistance of the ideal op-amp will be always 0. So all these characteristics about the op-amp, we can summarize them. We can summarize them quickly here. That for the ideal op-amp, the gain is infinity. In the linear region, Vp equals Vm. Then In equals Ip equals 0. And from here we find that I output plus IC plus IC minus equals 0 from Kirchhoff current law. Finally, R input is infinity, R output is 0. Okay? One question before we end this video. Okay, we'll postpone this question to the next video about R input and R output. But for now, remember, one thing before we end this video, that these two assumptions for the ideal op-amp in the linear region and in any region in general, this condition is in the linear if you assume linearity, and this condition applies all the time for ideal op-amp. These two conditions, keep them in mind. These are very important. These are the basis for our chapter here. You will use them to solve any op-amp problem. So any op-amp problem, you start by writing these two conditions. Okay, see you in the next video.